All right, question 7 says compute the circulation and flux integrals of the radial field F, which is xi plus yj, over the circle centered at the origin with radius a. Assume a counterclockwise parameterization for the circle. Okay, so you can see up here in this figure that at every point on our path here, this blue circle, our vector field, which is just this radial field, is going to be perpendicular to our direction of motion, okay? And it's going to be parallel to this outward pointing normal vector that we introduced in the last video, okay? So that's this vector here in purple that you see as you move along the circle. Okay, so for the circulation, right, this is just a sum of the tangential components of our vector field as we move along the curve C. And at every point, that tangential component is 0. So our circulation, it should be 0. We'll go ahead and do the calculation here in a moment, but for right now, we'll just comment that it should be 0. What about the flux? Well, that was a sum of all the normal components of our vector field as we move along the curve. And here, since the field is always parallel to this outward pointing normal vector, that's going to give us a positive normal component at every point. So when we go ahead and sum those all up, we should get a positive value. So this should be positive. Okay, so now let's actually do the calculations. So for our path here, R, I'll go ahead and parameterize this as A cosine A sine. This will give us a counterclockwise parameterization. We'll let t vary from 0 to 2 pi. And if our vector field F is xi plus yj, then to evaluate that field along our path, okay, this is going to equal what? Well, I'm going to set x to a cosine t. So that's just going to give us a cosine t. I'm going to set y to a sine t. So that's just going to give us a sine t. Okay, so now for the circulation, I want to compute this line integral of our vector field along the curve C. Okay, and so to do that, we're going to integrate from 0 to 2 pi. And we're going to do f of r of t dotted with r prime. And then we're going to integrate that expression with respect to t. Okay, so let's go ahead and punch each one of these in. So our f of r t is just right here. It's just the a cos t, a sine t. And then we're dotting that with r prime. And if this is r, then r prime will equal minus a sine t, a cosine t. Okay, so go ahead and put that in right here. And I can see that when I'm going to, what am I going to come out with here when I compute the dot product? Well, I'll get minus a squared cosine times sine, and then plus a squared cosine times sine. They're going to cancel out, which again agrees with what we've already said, right? We just based on the fact that our curve is a circle and our field is radial. Okay, the vector here in green will always be perpendicular to this tangential direction, and so indeed our circulation is 0. All right, so then for the flux, this is where we're going to compute the line integral of f dot n, this outward pointing normal, okay? And I had written this in the last video in terms of the components of our field P and Q. Let me show you how, And that's perfectly fine. It's a good way to do it. But I'm going to show you a way that's really similar to what we're already doing for the circulation integral. It's just going to have to be modified just slightly. So I'm still going to look at, of course, our field evaluated along our path. And now, instead of dotting this with the derivative vector, I want to dot it with what I'll call r perpendicular prime. So in other words, this is just going to be the derivative vector just rotated, so I get the vector that's normal and pointing outward. So what is r perpendicular prime? What is this going to be in components? Well, remember from the last video I said, okay, you just swap the components of r prime. So this would be a cosine and then negative a sine, but then we stick a negative in front of the x prime. So this is actually going to just be a sine in this case. Okay, now more generally, if your r prime is x prime, y prime, then your r perpendicular prime would be y prime comma negative x prime. Okay, so with that, let's go ahead now and compute this integral. So I'm going to take these two quantities and punch them into the integral. This can give us the integral from 0 to 2 pi, and then we're going to have our a cosine a sine. Then we're dotting that with r perpendicular prime, and so this is going to be a cosine t a sine t, and got dt. All right, so now when I do the dot product, what am I going to come out with? I'm going to get an a squared cos squared plus a squared sine squared. That's just going to all come out to be a squared. And if I integrate this constant, which is just the square of the radius of the circle, over the interval from 0 to 2 pi, I'm just going to get 2 pi a squared. Very nice. Okay, so as we noted here, the flux is positive, circulation is 0. Also, in the last video, we said that if you think about your vector field as, say, describing the flow of a fluid through some region, okay, then we're asking for circulation, right? How much of that flow is along the curve C, or in other words, how much of it is tangential to the curve C? Well, with our field here being radial, none of the flow is tangential in this case, so 0 circulation. How much is the flow here then going to be directly across the curve C, right? How much of it is normal to the curve C? And here at every single point, right, because of that radial flow, again, we see that that vector there in green is parallel to the normal vector. So you just get positive contribution with this outward flow all along the circle. Okay, so positive flux. Now to finish here, it says what happens to your answers if the circle is given a clockwise parameterization? Well, I've gone ahead and done that. I'm going to take that here. Okay, so I've just done all the steps. So the only change now is I'm going to give this circle a clockwise parameterization. So I'm going to let x equal a sine t and y equal a cosine t. So that's going to start us up at the top of the circle, and then we're going to rotate clockwise, make one trip around in the interval 0 to 2 pi. And so I've gone ahead and just computed all the key things we need. Again, the circulation will be 0, and that is not a surprise. Notice as we move clockwise now, okay, the vector here in purple, right, our unit normal is now pointing in to the circle as opposed to the outward direction that we saw with a counterclockwise parameterization. Okay, so nonetheless, this vector in green is always because it's radial, it's perpendicular to that tangential direction. So circulation should still be 0 as it is. Now the flux, though, that does change. And notice everything is essentially the same, except now we pick up a negative, right? A negative 2 pi a squared. And that's due to this. It's really a reverse in orientation for how we're moving around this path. Okay, so in the next video, we're going to discuss uh, parameterization for vector line integrals. And unlike scalar line integrals, as we see right here, the answer can uh, change. It really will change in sign like we're seeing here if you reverse orientation. So with that, I will see you in the next video. Thanks.